Hello everyone, we are Group Mechalysis from course Can P3373, Finite Element Analysis, semester 2, 2024-2025. Today we will be presenting our problem-based learning PBL video presentation on the design of ergonomic grass cutting tool. Hello everyone, my name is Cyril Anakiai and my metric number is X2498. Today I will present the final design of our grass cutting tool developed to solve issue faced by Unimas landscaping team. Currently, tools are heavy, fuel-powered, and uncomfortable to use. They often cause fatigue, back pain, and hand tremors. Our solution is a handheld battery power cutter using a 21-volt lithium-ion battery. It's lightweight, cordless, and quiet. The aluminum shaft makes it strong but easy to carry. We added a vibration damper handle and a padded shoulder strap to reduce strain and improve comfort. This tool is safe, practical, and ideal for long hours of use. Most importantly, it supports SDG9 by promoting innovation through sustainable, user-friendly design. Thank you.
Hi, my name is Muhammad Farid Ikmal bin Zainuddin and my metric number is 84611. So I will explain the finite element analysis we perform on the grass cutter shaft. We use Autodesk Inventor to simulate how the shaft behaves under top loading. The shaft is 1 meter long, made of aluminum 6061 and is hollow with a 50 mm outer diameter and 45 mm inner diameter. In the simulation, we applied a 5 Newton meter torque at the blade end to represent cutting force. The motor end was fixed to simulate real mounting conditions. A mesh was automatically generated and refined near the ends. The simulation showed a maximum von Mises stress of 4.617 megapascal and a maximum displacement of only 0.797 mm, which is very low. The safety factor was 15, meaning the design is very safe. We also did a hand calculation using torsion theory to get the theoretical stress in order to support the simulation results. Overall, the analysis shows that the shaft can safely handle the torque produced during grass cutting. So that's all from me. Thank you.
So, very good evening, everyone. My name is Joster, and I'm going to present on the calculation. So, as we could see here, we already had a fixed constraint which is located at the very left of the beam, which is connected to the blade. So, as you guys could see here, the reaction forces that are involved is in x and y direction. While for the x direction, the force is 18 negative 18.0041 Newton, and the force at y direction is negative 1.21 at 1. And for the reaction moment, we have negative 1.2195 for the moment at x, 18.0631 for moment at y, and also negative 5.004 for the moment at z axis. Other than that, we also included the calculation of bending moment of inertia for a um, for a shaft, for a beam, which is equivalent to I equivalent for pi over 64 divided with um divided with outer diameter times power of 4 minus with inner diameter times power of 4. Hence, we have our bending moment of inertia. Other than that, we also have our bending stress, which is at x it is 4.29 megapascal, while at stress at y is going to be negative 0.29 megapascal. Once the value of all of the unknown is had been made well made known, so we are going to use several type of stress. First one will be the von Mises stress. So this von Mises stress over here, we had calculate the item here, and from the product that we have shown here, so it will be half of the shear, it will be half of the addition from the shear stress, and actually is going to plus also with the it's going to be the same for the shear stress terms, while for the sum of shear, as we already seen here, it is going to be 4.57 megapascal, which is not far from the obvious or from the actual simulation done by FEA. Moving on, we're going to calculate the strain. So the elastic potential of this beam is around 69.9 gigapascal with Poisson ratio of 0.33. So we already plugged in the value inside here. Thus, we could see here that the strain at x is 0.00063. For the y, the one is around negative 0.00001 for at, and last but not least, at the z-axis, while the as we could see here, the 0 minus 0.33 times with 4.29 minus 0.29 divided with E elasticity. And for maximum displacement, we are going to use the sig allowance going to use ml square over at I. So in this, we apply the moment at 5,000 Newton meter. The beam length is 100,000 meter, and also for the Young modulus is 68.9. So when we calculate the moment of inertia, or we calculate the maximum displacement, it is only up to 0.00058 millimeter. That's all from me. Thank you.
Hello, my name is Carl Taro Frederick with metric number of 83419, and I'll briefly outline the additional standards that shaped our grass cutting design. Firstly, we adhered to ISO 6385 as well as ISO 9241 to make our lightweight frame, adjustable shoulder strap system, and handle geometry to optimize for the posture as well as the user comfort. For the next step, we used ISO 5349, which specifies the measurement methods and exposure limits for hand transpirate vibration. This directed our design of rubber brushings as well as anti-vibration padding to ensure that our users are remain well below the HEVS threshold. And finally, we use ISO 12100 for guiding our risk assessment as well as the integration of guards and interlocks to make sure that our device is safe to use. That is all. Thank you.
Now I would like to explain how our project supports Sustainable Development Goals 9, which is focused on industry innovations and infrastructure. At Unimas, maintaining the campus landscape is a major task, especially with a larger area of 1,000 hectares. Unfortunately, the existing grass cutting tools used by the landscape team are heavy and not ergonomic designs, which has caused injury and reduced manpower. Our team took this real-world challenge to turn into an opportunities of innovations, where we designed a new grass-cutting tools that is lightweight, ergonomic, and validate using finite element analysis or FEA to ensure that the tool is not only safe and durable but also efficient for a long-term use. This aligns with SDG 9, which promotes innovations and sustainable infrastructures. Through our project, we introduced a new and improved tool design, promoted safer and more sustainable work practice, and apply engineering tools like CAD and FEA to solve practical problems. Thus, our project shows how engineering solutions can contribute to global development goals and, in this case, support SDG 9 by innovating better infrastructures and productivity at Unimas.
That concludes our presentation on the ergonomic battery-powered grass cutting tool. We hope this innovation solution can improve worker safety, reduce environmental impact, and support sustainable practices on campus. Thank you for watching.